All right, welcome to the second half of Remote Learning 8, and we're going to do two free response questions from the AP Calculus AB test, both of which involve a differential equation, and both of which, upon first reading, can be quite scary, I think, mostly due to the terminology and the fact that we're now at a level where each problem is its own lesson. And I think we're also at a point here with this upcoming AP test where we're right on the edge of what is acceptable for them to do in terms of whether this is deemed to be covered curriculum. But I am going to err on the side of caution and work with these differential equation problems, even though I think that they're probably pretty complicated. Okay, so please do pay careful attention and afterwards pop in, do the meet, and we can discuss things further. I would love to do so because these are fun topics. Okay, so this is from the 2018 exam, and we're to consider a differential equation that is written as dy dx. So keep in mind that dy dx is the slope of the function. And we don't necessarily have the equation of that function, but we do have its derivative, right? So we know its, if you will, its slope calculator. And this slope calculator, this derivative, is dependent upon both the input and the output variable. So then that's unique to the style of differential equation. Okay, now in part A, they start talking about a slope field, and then that's new vocabulary, and then that's what this is over here. So let me explain a little bit about a slope field. A slope field is a really super helpful way of visualizing all of the various slopes on the Cartesian plane for the particular function, which in this case is in terms of two variables. So let me sort of re-say that by showing some examples. So as I mentioned, there is a slope calculator going on here. That's our derivative dy dx. So for instance, if we wanted to know the slope at, and I will use one of these 2 points that's marked here, say 0, 2, then I would have to put in a 0 for x and a 2 for y and compute. And when I compute, I get 0. So when I'm up at this point, the slope is 0. And you can see that they've already marked that with their little, it looks to be a minus sign. So if I pick any other point, now let's pick this other point that they've marked. That's 1, 0. So let's mark that one as 1, 0 and find its derivative. Find its tangent slope. So the slope of the line tangent to the curve at 1, 0. Now, remind you, I don't have a picture of the curve, but I have its slope calculator. Okay, so I put in 1 for x and 0 for y and compute. And what do I get? I get 4/3. So that's positive, and you can see that over here I'm at slope 4/3, slightly bigger than 1, slightly bigger than a 45-degree angle. Okay, so you can pick any x-y combination and you will get the corresponding slope, and then it is marked for you. So I can see that the slope at, something like -1, 2, 3, 4, 5, 6, 0 is going to be negative and steep, maybe something like -4 or -5 or something like that. Okay, so let me go on then to read the question and work on part A. So a slope field for a given differential equation, for the given differential equation, is shown below. I actually moved it up above, so it's this one. Sketch the solution curve that passes through the point 0, 2. Okay, so I'll stick with green for the point 0, 2. And we're to draw the original function, the solution curve, knowing that its slope at 0, 2 is flat, is 0. So then the curve is flat. And in fact, everywhere the curve is flat. All the tangent slopes are 0. So then this is the answer to the first part. I've sketched the solution curve that passes through the point 0, 2. Okay, so this might make a little more sense as I go on to the next one. So I'll switch colors for the next one. And as my curve goes through 1, 0, it has a positive tangent slope. Its tangent slope is 4/3, so it's going to be moving up in that direction. But then as it moves in that up direction, it gets to another point, and that slope is different, and it follows that slope for a while. Then it gets to another one, and it follows that slope for a while, and so on. And so you really just end up tracing these various tangent slopes. So this one leads us to here, and then we follow that one. Okay, so we got a minimum value there, and okay, it's a tracing exercise. And believe it or not, we've just answered 6A. So there we go. One more time. A slope field for a given differential equation is shown above. Sketch the solution curve that passes through the point 0, 2. So I went to 0, 2, and I followed its slope until I reached another slope, which was flat, and then that one was really boring. This one was a little more exciting. I went to 1, 0, and I followed its tangent slope until I got to a point where the tangent slope was different, and it's tapered me off, and then, well, I did it in little pieces and followed it backwards. Okay, so slope fields, and maybe the main concept is, not to lose sight that this is the derivative, is the rate of change of y with respect to x. We've talked about that as, the slope calculator, the tangent slope calculator. Okay, so let's move on then to part B. So let's see, for part A, I guess that was C graph. And for part B, we're to let y equal f of x be a particular solution to the given differential equation with initial condition f at 1 equals 0. So for the function that we haven't found, which would be y, or you could call it f at x, it has this initial condition that when you put 1 into it, you get out 0. So we call this the initial value or the initial condition. Okay, so write an equation for the line tangent to the graph of y, which we don't know what it is, at x equals 1. Use your equation to approximate f at 0.7. Okay, so one thing at a time. Write an equation for the line. This sounds like an Algebra 1 problem, right? Find the equation of the line, and then they give us some information about the line. So one thing that they give us is a point that is on it. That is the point 1, 0. Right? So write the equation of the line tangent to the graph of the function we don't know at x equals 1. Well, we know when you put in 1, you get out 0. So then they give us a point on our line. So in order to find its equation now, we just need to know its slope, and we have the slope calculator from up above. Okay, so I'm going to go get that slope calculator and bring it down here. Oops, that's not it at all, actually. That was just on the clipboard. Well, I can rewrite it, and that's not too troublesome. Okay, so in order to find the slope of our tangent line at a particular point, say 1, 0, we need to drop those values in. And I already did that up above. So I'll go heck fast. And that was 4/3. Okay, so if you want to think about this in an algebra 1 way, that is our m value. Okay, and then we also know that we're on point 1 comma 0, so we'll use the point slope formula and find the line tangent to the graph's equation. So that'll be y minus 0 equal its slope times x minus 1. All right, so y equals 4/3 x minus 1 answers the question. So let's just read it one more time. Let y equal f at x be the particular solution to a given differential equation with the initial condition f at 1 equals 0. Write an equation for the line tangent to the graph. So as soon as they start talking about write an equation for the line, I'm thinking y equals mx plus b, and I need to know a few things in order to do that. Like I need to know its slope and 1 point on it, whether that's the y-intercept or not. Okay, so then I was able to find its slope because they gave me the slope calculator, dy dx, and rather conveniently an x and a y value that live on the line. So, okay, I used that point twice, once to find the slope and once to build the rest of the line's equation. Okay, so then we have a scenario where we have, I think it's probably best to go back up to the picture. Okay, so we have a scenario where we just found this line. It's equation, okay? So that's 4/3 times the quantity x minus 1. Okay, so we're now to use that equation to approximate the function up there in red that we don't know the equation of, but we've drawn it nonetheless, at 0.7. So the idea is that since we have the equation of the black line, and the black line rides the red curve near to 1, 0, we can find points on the black line, and that will approximate points on the red line in that vicinity. Okay, so I'm not finding f at 0.7. I am finding this line's output at 0.7. So that's the second part of this. So then that's real easy. You just drop in 0.7. Okay, so then what do we get? We get 4/3. That's negative 0.3. So that's 4/3 times negative 3/10. And that's negative 2/5. Okay, so maybe you want to get that into a decimal. That's negative 0.4 if you want. Okay. All right then. So then let's go on to part C. And part C asks us to find the particular solution y equals f at x to the given differential equation with initial condition f of 1 equals 0. Okay, so then this is said differently to find the equation of the red curve from up above. Right, so find that particular sort of a reverse bell curve function. All right, so then let's dive into this. And this is going to be in line with the type of work we did in Remote Learning 8, Part 1. Let me bring my function over, and we will move towards finding its particular solution by finding its general solution first, and then using the condition that's provided. All right, so our differential equation was that dy dx equaled 1/3 x times y minus 2 squared. So first I'm going to separate the variables by leaving the dy on this side and dividing each side by y minus 2 squared, and by also multiplying each side by the dx. All right, so then it's time to do the usual integrate throughout. And over here on this side, you could do a u sub, but it seems like, as usual, they give us something nice and linear in there whose derivative is 1, so we can move more quickly through this. And maybe it's worth writing it at least as y minus 2 to the negative 2. And over here, I'll just do a little precursor work and pull out the constant. Okay, so reverse power rule, and that's now to the negative 1 power divided by negative 1. So there's that side. And then over here, 1/3 x squared divided by 2. So I'll write it like that, and then plus the constant. Okay, so let's see about making some room here. I now have negative. You know what? I'm going to go back to a fraction because I see a bunch of algebra coming at some point. It might be a little bit easier to do it that way. So what am I going to call this? Negative 1 over y minus 2 equals 1/6 x squared plus c. Okay, so that's the general solution, and then I'm going to go and find c by using this initial condition, which is input 1, output 0. So that makes negative 1 over negative 2 there, and over here it makes 1/6 plus c. So what is that? That's 1/2 minus 1/6 is c, and c is 2/6 or 1/3. Okay, so then I'll just see about continuing down here. I now have the particular solution, which is negative 1 over y minus 2 equals 1/6 x squared plus 1/3. All right, but I am supposed to isolate the y, so that's what's going to come next. And let's see, what's a good way to do it? Well, I want to flip this one around. I need this to be a single fraction, so I'm going to leave this alone for the moment and get a common denominator over here. So what's that? That's going to be 6, and that will become x squared plus 2. Okay, so that allows me to reciprocate that side and take the reciprocal on that side as well. Okay, so there you go. And let's get rid of that negative, multiplying each side by a negative. And finally, add the 2, and I'll introduce the f of x notation as well. Okay, so this looks to be the final answer, but I want to go back and read it one more time. Okay, so find the particular solution, y equals f of x. I do have y in terms of x's. To the given differential equation that was given away in the early part of the problem with the initial condition 1, 0. All right, and then that's a classic particular solution problem. And I did the usual things: separation of variables, all the y's on one side, all the x's on the other, integrate throughout, that's the red move, very carefully integrating because you don't want to make a mistake early on, and don't forget the plus c. Officially speaking, there's a plus c on each side, but then when you merge them together, you really just get a constant, so you can write plus c only on the one side. Now then, you could either play a bunch of algebra and solve for y with the c running around as a constant, but I find it easier to get the c sort of taken care of first, so then I just went ahead and used the initial condition and dropped in the 1 and the 0. Okay, c is a third, and And then once I have the particular solution, just have it in the wrong format. So then the rest of it is another algebra problem to isolate the y value. Okay, so then that was that one involving differential equations. All right, I'm going to try to squeeze one more in our lesson here, and I've got about 10 minutes, so let's see what I can do. Right. As usual, I am suggesting that you pause it and read and think, and then I will proceed after you do that. But in my world, I'm just going for it. So here we have, at time t equals 0, there's a potato, and it's taken from a pot on a stove and left to cool in the kitchen, so it's a hot potato. The internal temperature of the potato is 91 degrees Celsius. So what is that? I don't know, but it's hecka hot because 100 degrees Celsius is boiling. So, don't touch it. It's hot. And okay, and then it cools, right? So, and the internal temperature of the potato is greater than 27 degrees at all times. Okay, so fine. It's going to cool down, but for this particular problem, it's not going to go any colder than 27 degrees Celsius. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies the differential equation dh dt equals -1/4 the quantity h minus 27, where h at t is measured in degrees Celsius, and for that matter, h at 0 is 91. Okay, so again, I think upon first reading, it's pretty concerning. There's just so much going on. Okay, so if I could just start taking a couple of deep breaths and think this through. One thing that's going on over here with this differential equation is that this is the derivative of h with respect to t, and our function is in terms of h. So let's sort of remember that as we go forward. And what does h do? H is this function that you put in the number of minutes, and then it tells us the degree of the potato, and the potato is cooling. Okay, so what we have then is we have the rate of cooling with respect to time. And the rate of cooling in this case depends upon the function itself. So we've sort of wrapped ourselves in a little knot. Okay, but let's see what we can do. The first thing is to write an equation for the line tangent to the graph of h, which this is not the equation of. I do not know the equation of h. But we're to write the equation of the line tangent to the graph of h at time equals 0. Okay, so one thing that came out in the other problem is that if you're asked to do an Algebra 1 problem, find the equation of a line, you need to know its slope. Good news, we do have a slope calculator, and you need to know one point on it. And we have a point on it because they gave us this initial value for h itself, that at 0 the temperature is 91 degrees. Okay, so then I really need to go find its slope. So I'm going to go find the slope of h at time 0 next. So that is a matter of evaluating this at time 0 and temperature 91. Well, if I look at my formula, it doesn't involve the time, it only involves the temperature. So then I'll just put 91 there. Okay, and then do that computation. And okay, I'm going to do that computation rather quickly on my calculator. So what do I got here? 91 minus 27. Oh, that's kind of convenient. Is 64. Divided by 4 is 16, and then don't forget the negative sign. Okay, so then that is my slope at 0, 91. So you've got to imagine that there is some curve that we don't know the equation of, that's h. And then butting up next to that curve h at 0, 91 is a tangent line, and that tangent line slope is negative 16. Okay, so putting this all together in point slope form, the answer to the first part of this is y minus 91 equals negative 16 times x minus, and then that's a 0. Okay, so let's see. That, oh, you know, and I should be using t and h's, if you don't mind, now that I think about it. So that's h and that's t. So maybe I'm gonna want to rethink that actually, because this isn't the function, this is the line that butts up next to it. Yeah, but they think that's all right because we still have t as the x-axis and h is the output axis. So yeah, I'm sticking with my h's and t's. Okay, so let's see, what is this? Negative 16t plus 91. Okay, so if we would like to talk about this as h at t, that'll be fine. Okay, but that is not the function, that is the line that butts up next to the function. Okay, so let's see. Use this equation to approximate the internal temperature at time 3. Okay, so internal temperature at time 3 is negative 16 times 3 plus 91. And so what is that? Negative 16 times 3 plus 91. That's 43 degrees Celsius. So rolling on to the second part of this problem, part B, where again I think you should pause the video and think about this problem before I do it. It says to use the second derivative of h with respect to t to determine whether our answer from part A, this 43 degrees Celsius, is an underestimate or an overestimate of the internal temperature of the potato at time 3. Okay, so what we need to consider on this one, since the second derivative tells us something about concavity, we could consider the two cases. So if it's a scenario where it turns out to be concave up, so let's get that scenario going. If it was concave up, then our 091 would be somewhere over on this side, so that the tangent line was negative, because we see that as negative 16. Right, that's the slope of it. And this would be the point 0, and 1, 2, 3 would be somewhere over on this side. So if that was the point 0 up 91, you know, you could say that 1, 2, 3 is somewhere over here. And then you would see that R value, which is on the line, would be an underestimate. Okay, so if it turns out that it's concave down, then our 091 is somewhere on this side, so that the tangent slope again is negative, so something like negative 16, right? And then 1, 2, 3 is out here somewhere, further to the right. And in this case, our value 43, which is up on the line, is above our actual value. So in which case, then we have an overestimate. So we need to determine the concavity. Okay, so concavity is dependent upon whether or not the second derivative is positive or negative, so at a particular point. So then let's investigate that part of things. Okay, so the trick here is that the original function, the original differential equation, which is dh dt equals negative 1/4 h minus 27, is a function of h, not a function of t. So we need to think about this as a function of t, so that you see the chain rule coming. All right, so then if I am to take the derivative with respect to t on each side, over here on the left side, I'll have generated the second derivative, which tells us about concavity. And over here, I'll differentiate using the chain rule. So if you can visualize distributing the negative 1/4 in there, I have negative 1/4 h, and then the derivative of that is negative 1/4, plus the constant that goes to 0. But then by the chain rule, we need to take the derivative of h. All right, so then I have negative 1/4 times, and we have dh dt again, and we know what dh dt is. Okay, so now I've got 1/16 h minus 27. All right, so at this point, you could argue that we have a scenario where the value of our second derivative is greater than 0. This is because it did state up in the problem that the temperature was always greater than 27. So regardless of the amount of time that's passed, the temperature is greater than 27. So this is a positive number. This is a positive number. So the whole thing is positive. All right. So then that is therefore implying that things are concave up. Remember, again, that when a second derivative positive, your first derivatives here in red are increasing, going from negative to positive. So we're in this scenario where the tangent line runs below the function 3 spaces over. So we can see that this 43 is actually an underestimate. So I'll just write underestimate. 43 degrees Celsius is an underestimate. All right, so I do realize I'm a little over on the time, and part C is going to take more than just a few minutes. So let me bring it up here and decide if I want to have this turn out to be the homework problem associated with the second half of our lesson today. Yeah, so I think this is going to work out nicely. I think with the lesson from the first half of today, part, was it D from this earlier problem? No, part C from the earlier problem, and what I've just gone over on this problem, you should be able to do part C as the homework problem associated with the second half of today's lesson. Okay, so I'm just going to write that out here, and that's a wrap for today.